Acid-base disorders. The classification of acids and bases can be classified generally into two major categories. The first is based on hydrogen ions, which is invented by Bronsted-Lowry. According to this, acid is defined as a substance that can donate hydrogen ion, while the base is a substance that accepts hydrogen ion. Another definition is based on the donation of pair of electrons, which is invented by Lewis. According to this, acid is defined as a substance that accepts pair of electrons, while base is a substance that donates pair of electrons. A third category of acid-base, which is very less used, is the ability of substance to increase or decrease the concentration of hydrogen ion in solution. This is invented by anhydrous. According to this, acid is a substance that can increase hydrogen ion concentration in a solution, while base is the substance that can decrease hydrogen concentration in a solution. Though the classification based on donating pair of electrons is a wider definition, however, for our discussion regarding acid-base disorders in humans, the classification based on donating hydrogen will be used. According to the donating of hydrogen ion classifications, acids can be classified as strong or weak, depending on their speed of donating hydrogen ions. Strong acids are those substances that can donate hydrogen ions rapidly, while weak acids are those substances that donate hydrogen ion relatively slowly. An example of strong acid is hydrochloric acid, and an example of a weak acid is carbonic acid. Weak acids could act as buffers. Similarly, bases could be classified as strong or weak bases, depending on their speed of accepting hydrogen ion. An example of strong base is hydroxide, and an example of weak bases are bicarbonate, phosphate, and proteins. Weak bases could work as a buffer also. Hydrogen ion is precisely regulated in extracellular fluid to achieve a concentration of 0.00004 milliequivalent per liter. This precision of hydrogen ion reflects the critical role and impact of hydrogen ion concentration on cellular functions. The letters pH are an abbreviate for bondus hydrogeni, which could be translated as hydrogen power. This abbreviation is used to describe the acidity of a solution, as acidity is measured by hydrogen concentration. This means that pH is simply the hydrogen ion concentration and can be written as pH equal to the log of hydrogen ion concentration. The use of logarithmic rather than absolute number was invented by Sorenson to avoid using numbers with a lot of decimals. Accordingly, the solution which contained 0.0000007 or 10 to the power of -7 of hydrogen ions have a pH of 7. Since we are using the logarithm for pH calculations, then the differences are exponential. For instance, comparing pH of 7.5 to pH of 6.5, the hydrogen concentration of 7.5 is 10 times less than 6.5. This reflects that minor changes in pH figure reflects more prominent changes in hydrogen concentration. Henderson-Hasselbalch equation is used to estimate the pH. The equation states that pH equal to the pKa plus the log of base divided by acid. pKa is a standard dissociation rate between carbon dioxide, bicarbonate, and carbonic acid, which is equal to 6.1. So the equation could be restated as following. pH equal to 6.1 plus the log of the base divided by acid. Base is represented by bicarbonate, while acid is represented by partial pressure of carbon dioxide. 0.03 is used here as a correction factor, as the solubility of carbon dioxide in physiological fluids is 3%. Hence, and according to Henderson-Hasselbalch equation, the pH in arterial blood is a function of bicarbonate and carbon dioxide. Thus, an increase in bicarbonate will result in an increase in pH, or alkalosis, and vice versa. A decrease in bicarbonate will result in a reduction of pH, or acidosis. Using the same equation, but looking at partial pressure carbon dioxide, an increase in partial pressure carbon dioxide will result in lowering pH, or acidosis, and vice versa. A reduction in partial pressure of carbon dioxide will result in a higher pH value, or alkalosis. Important conclusion can be drawn from the equation, which is the ratio of bicarbonate to partial pressure of carbon dioxide, is what determines the pH, not the absolute number. The normal ratio between them is 0.6 to 1, and that will keep pH equal to 7.4. In a clinical laboratory, we usually measure pH and partial pressure of carbon dioxide, while bicarbonate concentration is calculated using this equation. The pH of arterial blood is normally maintained within 7.35 to 7.45, or more narrower range between 7.36 to 7.44. Any value of 7.35 or lower are termed acidemia, and any disorder causing acidemia will be termed as acidosis. And any value of 7.45 or higher are termed alkalemia, and any disorder causing alkalemia will be termed as alkalosis. Though patient status and underlying factors dictate the urgency of treatment, however, in general, pH values of less than 7.2 or higher than 7.6 represent levels that require proper treatment to reverse the situation. Compensation for pH alterations. If pH altered, whether it's above or lower the normal range, then the body reacts to correct this abnormality. The first response is to use the chemical buffering system in blood. Second, by using ventilatory adjustment by the lung. And third and finally by alterations in acid excretions by kidney. With estimated average daily production of 13,000 milliequivalent of hydrogen ions, kidney is responsible for less than 1% of the acids. Hence, acid-base disturbance will not occur before long period of renal failure. However, cessation of breathing for minutes could result in acid-base disturbance. Chemical acid-base buffers. Chemical buffers are available both intracellular and extracellular compartments. There are three systems recognized yet, and these are bicarbonate system, phosphate system, which is found in renal tubular fluid and in intracellular, and proteins. Bicarbonate available in extracellular are in the form of sodium bicarbonate and carbonic acid, while in intracellular it's available as carbonic acid or potassium bicarbonate. Bicarbonate system is the most powerful system in extracellular, while proteins is the most powerful in intracellular spaces. All buffer systems exist in equilibrium, so any change in acid-base status is reflected equally in each system. Hence, the measurement of any system will accurately measure overall acid-base system. Chemicals that will be used by buffering system are as following. This is the chemical formula and chemical structure, which consists of one central carbon atom surrounded by 3 oxygen atoms in a trigonal arrangement with a hydrogen atom attached to the one of the oxygen atom. Bicarbonate is a weak base. This is the chemical formula and chemical structure of carbonic acid, which consists of one central carbon atom surrounded by 3 oxygen atoms in trigonal arrangement with 2 hydrogen atoms attached to the 2 of the oxygen atom. Carbonic acid is a weak acid. Carbon dioxide chemical formula and structure are presented here. Carbon dioxide is a weak acid. When bicarbonate bind to hydrogen ion, they form carbonic acid, which is in turn, and with the catalysis by enzyme carbonic anhydrase, it is converted to carbon dioxide and water. Hydrogen ions, which is an acid, is released as a result of cellular metabolism. And if the release of hydrogen ion continue, this will lead to lowering pH. So, the buffer system works by binding the base, which is the bicarbonate, to hydrogen ion, and thus prevent the reduction of pH. Virtually, all carbonic acid, which is an acid obviously, is transformed to carbon dioxide and water. Thus, an increase in hydrogen ion will result in reduction in bicarbonate concentration due to binding process, and that will result in a higher concentration of carbon dioxide. Normal arterial blood gas values are as following. pH is 7.4 with a range between 7.35 to 7.45. Partial pressure of oxygen is between 80 to 100 millimeter mercury. The saturation of oxygen is 95%. Partial pressure of carbon dioxide is between 35 to 45 millimeter mercury, and bicarbonate between 22 to 26 milliequivalent per liter. Upon receiving the lab result of arterial blood gas of a patient, the readings might be normal or below the normal, and in this case we call it acidemia, or above the normal, and we call it in this case alkalemia. In case of acidemia, if the primary reason for pH reduction or acidemia is an increase in concentration of partial pressure of carbon dioxide, then we call it respiratory acidosis. And if the primary reason for pH reduction of acidemia is decrease in bicarbonate, then we call it metabolic acidosis. Similarly, in case of alkalemia, if the pH increase or alkalemia is a result of primary reduction in partial pressure of carbon dioxide, then we call it respiratory alkalosis. And if the primary reason for alkalemia is an increase in bicarbonate, then we call it metabolic alkalosis. It is important to differentiate between primary reason and compensatory mechanism. For instance, if there is a respiratory acidosis where there is a primary increase in a partial pressure of carbon dioxide, then compensatory mechanism will also increase bicarbonate level. Since the compensatory mechanism is not complete, we should look at a ratio of increase or decrease in partial pressure of carbon dioxide and bicarbonate. It is important to differentiate between simple and complicated acid-base disturbance. If only one out of these problems exist, whether it's respiratory acidosis or alkalosis, or metabolic acidosis or alkalosis, we call it simple or uncomplicated. However, in case of existing of more than one of these disturbances, then it is complicated acid-base disorder. To differentiate the problem of acidosis or alkalosis, whether it's respiratory or metabolic, and as Henderson-Hasselbalch equation states, that pH change is a result of change in partial pressure of carbon dioxide and or bicarbonate. So, if the reason for acid-base disturbance is partial pressure of carbon dioxide, then we call it respiratory. And if the reason for acid-base disturbance is bicarbonate, then we call it metabolic. To summarize reading arterial blood gas results, in case of simple acid-base disorder, we will recall Henderson-Hasselbalch equation for easy reference. In case of acidosis, whether it's respiratory or metabolic, and by definition, we will have low pH value. It is the same with alkalosis, whether it's respiratory or metabolic, and also by definition, we will have high pH value. It is important now to differentiate between primary disturbance and normal compensatory mechanism used by the body to lessen the effect of acid-base disorder. In case of respiratory acidosis, and since the problem is originated from the lung, then the problem with carbon dioxide. As per the Henderson-Hasselbalch equation, partial pressure of carbon dioxide have to increase to cause reduction in pH value. In the clinical sense, it is stated opposite, where an increase in partial pressure of carbon dioxide is the cause of reduction on pH value or acidosis. As a compensatory mechanism, and to minimize the difference in the ratio of bicarbonate over carbon dioxide, an increase in partial pressure of carbon dioxide will be associated with increase in bicarbonate, which results in minimizing the acidemia effect induced by increase in partial pressure of carbon dioxide. Accordingly, we will have higher value of bicarbonate as compensatory mechanism. Similarly, when there is a metabolic acidosis, which means there is a primary reduction in bicarbonate, which leads to reduction in pH value, compensatory mechanism will lead to reduction in partial pressure of carbon dioxide to minimize acid-base disturbance. Following the same concept, respiratory alkalosis will result from primary reduction in partial pressure of carbon dioxide, which lead to higher pH value with a compensatory mechanism of reduction in bicarbonate to minimize the effect. The same with metabolic alkalosis, which results from primary increase in bicarbonate, which results in a higher pH value and a compensatory mechanism of increasing in partial pressure of carbon dioxide to minimize the acid-base disturbance. It's important to note that in any case of primary disturbance, whether it's in partial pressure of carbon dioxide or bicarbonate, the compensatory mechanism works by following the same direction of increase or decrease in partial pressure of carbon dioxide or bicarbonate respectively. In other words, any increase in partial pressure of carbon dioxide will lead to increase in bicarbonate as a compensatory mechanism, and vice versa. To have more understanding of how this chemical buffer system works, let's recall our Henderson-Hasselbalch equation and carbonic acid bicarbonate buffering system discussed earlier. Let's take an example of respiratory acidosis, where there will be a primary increase in partial pressure of carbon dioxide, which leads to lower pH value or acidosis. Higher partial pressure of carbon dioxide means higher concentration of carbon dioxide, and this will lead to higher rate of binding between carbon dioxide with water to form more of carbonic acid, which in turn dissociates into hydrogen ions and bicarbonates. This results in higher concentration of bicarbonate, or the compensatory mechanism of increasing bicarbonate as a result of primary increase in partial pressure of carbon dioxide, which minimize the acid-base disturbance. Respiratory acidosis or alkalosis can be acute or chronic, while metabolic acidosis or alkalosis can be only chronic. When respiratory disorders continue for minutes to hours, it's considered acute, while if it's for days or longer, it's considered chronic. Metabolic acidosis. Although whenever we use anion gap, most likely we are referring to serum anion gap, but still, urine anion gap is still exist and have some clinical impact. The basic concept behind the use of serum anion gap is the fact that in order to maintain electroneutrality, then the concentration of cations in the serum must be equal to the concentration of anions. Cations includes all positively charged atoms or compounds like sodium, magnesium, calcium, potassium, while anion includes all negatively charged atoms or compounds like bicarbonates, chloride, proteins, sulfates, and phosphates. However, in routine clinical practice, some of the cations measured, like sodium, and others are not measured, like magnesium, calcium, and potassium. It is the same with anions. Bicarbonates and chloride are measured, while proteins, sulfates, and phosphates, plus others, are not measured. Because some of the electrolytes or compounds are not measured, the measured cations are more than the measured anions. So, if we calculate the difference between measured cations and anions, we will find a gap. This gap represents the difference between unmeasured cations to the unmeasured anions. Hence, if we calculate the difference between sodium as a cations and chloride plus bicarbonate as anions, the result should reflect the difference between unmeasured cations to unmeasured anions. The unmeasured anions is normally exceeding unmeasured cations. The normal range for this difference is between 3 to 11 milliequivalent per liter. This value might differ from institution to another due to equipments and material used, so it's important to use the institution normal range. Upon the calculation of serum sodium, chloride, and bicarbonate, we might have a result above the upper normal range, and we call it increased anion gap, or the result might be within the normal range. Generally, increased anion gap is a result of presence of indigenous acids which consumes bicarbonate, leading to lower level of bicarbonates and hence higher serum anion gap. Actually, elevated serum anion gap confirms metabolic acidosis regardless of the reading of pH or bicarbonates. In cases with normal anion gap, then it suggests that bicarbonates is losing from extracellular fluids and in this case is replaced by chloride. Hence, decrease in bicarbonate will be associated with increase in chloride, keeping serum anion gap within its normal range. The serum anion gap may be artificially lowered by decreased serum albumin, multiple myeloma, lithium intoxication, or profound increase in the serum potassium, calcium, or magnesium. Increase in serum anion gap could happen in the following situations: lactic acidosis, diabetic ketoacidosis, renal failure, methanol ingestion, ethylene glycol ingestion, salicylate overdose, and starvation.